Now the second mechanism of charge transport is something called as diffusion. Now what do you mean by diffusion? While the driving force for what do you say, drift based conduction is the electric field, the driving force for diffusion based conduction is the concentration gradient. Okay. So if you were to pass by a bakery, for example, okay, and if it's a really nice bakery and it's a warm day probably, you will find that you get a lot of sweet scents that are sort of in the air. Even though you are not at the bakery, you do get a whiff of all the sweet scents in the air, and that has got to do with all the molecules from all the sugars and everything else that is used in the bakery sort of diffusing through the atmosphere and ending up being sensed by our nose. Of course, there is a big difference. Those molecules are all neutral species and their diffusion is defined by slightly different parameters, but what we are interested in is the diffusion of charged species, which are electrons and holes, and the diffusion of these species has got is basically driven, or the flux of these the flux due to diffusion is because there exists a difference in concentration. So if you go back to your drift, we saw that the drift is because of a potential difference, right, but you can imagine the electrons. Okay, so if you have an electron concentration which is very large in say this area, you have lots of electrons here and you have got very little electrons there. Now it is very there is a tendency for these electrons to move or migrate towards this low concentration region, and that is what diffusion is. But if you think about it, a presence of a lot of charged particles here implies that this region has got low voltage, lower potential as compared to this region, and therefore in the case of charged entities, the diffusion can be thought of some kind of a self induced drift. Okay, it might be a wrong way of thinking about it when it comes to other matters, but here it does help the understanding if that in some sense. Okay, but essentially the driving force for diffusion is the concentration gradient. So let us try to derive the diffusion current. Okay, the diffusion current. So to start off, let's say we only talk about electrons, and let's say with distance x. Okay, so that's my distance. It's just one dimensional case. That's x increasing, and you have a concentration of electrons that is varying with space. We have just drawn this little squiggly line which is to indicate the electron concentration. That is the number of electrons per unit volume that is varying with x. So your dN by dx is greater than 0, which means as x increases, my electron concentration is increasing, because this is the direction of increasing x. Now these electrons in the semiconductor, so let us say there does exist a situation of this kind. Now if you look at all these electrons here, you got lots of electrons here, so that is basically all the electrons there, and you got fewer electrons here. Okay. Now these electrons have got some thermal velocity. We have not applied any voltage. Okay, so there is 0 voltage or 0 electric field being applied. These electrons simply have thermal velocity. Okay, and what is thermal velocity? In one dimension, your thermal energy by 2. Okay, so it's only a 1D case. So kT by 2 is equal to your half effective mass of the electron into V square, and your V is your thermal velocity, which is kT by me star square root. So all the electrons have a velocity of this value, and this velocity is in an arbitrary direction. So if it is a one dimensional case, some of the electrons are moving this way, some of these electrons are moving this way, and similarly on this side you have few electrons moving this way and few electrons moving that way. So, this this is the situation we are looking at. So, our interest is to look at a very specific region, okay, and as these electrons are moving through, they are colliding with the lattice. So, there is a mean collision time, and we had defined this mean collision time when we defined mobility, right. So, the electrons collide with the lattice, and therefore, it is only within this mean collision time that the electrons actually see an acceleration, okay. So, if you think about the when we had looked at mobility, when we had looked at mobility, we defined the mobility in terms of the mean collision time, okay. So, this is the time between any scattering event, okay, between any two consecutive scattering events, statistically speaking. So, we are interested in a boundary that is defined by this value L. So, x equal to L, which is equal to the thermal velocity of the electrons into the mean collision time. So, the electron moving with a certain thermal velocity travels this distance before it scatters, okay. So, that's the boundary we are looking at, and what we are interested in identifying is the total number of carriers that are going to effectively move from left to right and from right to left and cross the plane of x equal to 0. So, we want to get a count of these carriers, okay. So, since half the carriers are moving left, so if you take the x equal to, let us start with x equal to minus L, let us start with this boundary, okay, the leftmost boundary. So, if you get a count of how many carriers are moving in the towards the right side, okay, that is towards x equal to 0, it is half the number, okay. So, we will say that n by 2 carriers are moving towards the right, and they all have a velocity of Vth. Therefore, the effective flux or the number of carriers per unit area that are moving in a given time interval from left to right is n at x equal to minus L into Vth by 2, okay. So, that is the approximate average number of carriers moving from this boundary to the right. And since they are not going to have any scattering events, all these carriers are going to cross this x equal to 0 plane, right. Now, what about the number of carriers moving from the right to the left, okay. So, that is going to be n, the carrier concentration at x equal to L into Vth by 2, because half of them are going to be moving towards the left, and once again everything that starts moving towards the left is going to cross the x equal to 0 plane, because there are no scattering events, and that was the purpose of taking the mean collision time into this definition. So, therefore, the effective flux from left to right is basically this particular term, which is this flux, which we will call it flux left to right, and this is flux from right to left, okay. So, the flux from left to right effectively is the flux from left to right minus the flux of carriers from right to left. So, that is the effective number of electrons moving from left to right, and that is given by n at minus L minus n of L into Vth by 2. Now, if we know the carrier count at n at x equal to 0, so let us say, so this is the carrier gradient, right, and these are two boundaries, and that is your x equal to 0 plane. Now, if you know n at x equal to 0, which we will call n of 0, the value of the carrier concentration at n at of n, the carrier concentration n of L is simply n of x equal to 0 plus the slope into this distance L, right. So, it is n of x equal to 0 by dn by dx into L, or if you want, you can think of it as a Taylor expansion. Similarly, the carrier concentration here n of minus L is n at 0 minus dN by dx into L, okay, because the way we have drawn it dN by dx is positive and therefore these equations fit the physical picture. So this is the carrier concentration at minus L and L written in terms of the carrier concentration at x equal to 0. Now if you simply add these up, these two terms disappear and you end up with this particular term defining the effective flux from left to right. And we will now replace this L, okay, with Vth into T collision to get you this relation. So this relation tells us that there is an effective flux from left to right which is dependent on dN by dx and the square of the thermal velocity which is a constant and the mean collision time which is also a constant. Therefore the driving force is dN by dx. Now to understand this better, so that is the effective flux, right. So that is the flux. What is the total charge, that is a rate of change, that is the number of electrons moving from left to right per unit time, because you have taken into account Vth. So it is a flux per unit time. So the total current is simply the charge transiting per unit time, which is q times that flux, okay. So it is simply q times dN by dx into Vth square into T collision. Now what is Vth square? We had already defined Vth square as, since it's what do you say, 1D case, your half mean ME Vth square was equal to kT by 2, or Vth square is equal to kT by m, where the m is the effective mass of the electron, or m star, where m star is the effective mass of the electron. So we will replace Vth square by this term kT by m star, and therefore we have the total current due to the concentration gradient from left to right being equal to this particular term. Now note what happened to the negative sign. The negative sign, so if you look at the previous page, there was a negative sign here, okay. That was to do with the effective flux, because there are fewer electrons here and more electrons there, therefore it is understandable that the effective flux was in this direction. But then the electron charge is also negative q, it is minus 1.6 e minus 19 coulombs, which is equal to minus q, okay. So we have removed the negative sign by having a minus q into this negative flux, which is basically telling you that the current is positive. So you have all the electrons drifting this way, which means that there is a positive current going on from left to right. Now to this term we will add in, we will try to replace these two terms of m and T collision by the parameter mu, okay. So if we remember, how does mu connect to T collision and the effective mass of the electron, okay. So if we just step back, okay, and look at what is mu. Mu is nothing but it is the constant of proportionality for the drift velocity and the electric field. So the drift velocity is mu times the electric field, right. So although we are discussing diffusion, we need to step back and understand what mu is and how it is connected to m star and T collision. So it does not mean that this process is dependent on an applied electric field. There is no need for any applied electric field. It is only to understand mu better that we need to sort of step back. And if you apply an electric field, the total force experienced by the electron is this, which you can say is the rate of change of momentum of the electron. So it is m star into v drift by T collision, and therefore v drift was q T collision by m star into electric field, where this term is the mobility, okay. So that is the definition of mu. So if I were to apply a field to the semiconductor, the carriers would move with this drift velocity, but right now we are not applying a field, but nevertheless this relation still holds in the sense that T collision by m star is nothing but mu divided by q. Okay. So, that is what we are going to use that relation and replace this ratio of T collision by m star with mu by q. Okay. So, we replace T collision by m star with the relation mu by q in order to get this particular expression. Now, this term in bracket has got a very special significance, okay, and it is called the diffusion coefficient, okay, and is denoted by the symbol capital D. And since we are talking about electrons here, this is the diffusion coefficient of electrons, okay, we will call it dn. So, you could also call that mu n. So, therefore, the diffusion current can be written as q dn by dx. Okay. So, this dn is nothing but the capital D subscript n, which is the diffusion coefficient for electrons. Similarly, we could define a diffusion coefficient for holes and therefore define a diffusion current for holes. Now, if I were to have a similar profile, if I had to have a picture of P and if I have a flux, if I have a concentration gradient, you will find that all the holes are moving from right to left, because that is because they have got a higher concentration on the right and lower concentration on the left, and therefore, the current from left to right will be negative. Okay. Now, the electron current, the negative sign disappeared because the charge was negative, but in the case of holes you have a positive charge, and therefore, if the flux is in this way, the current from left to right is a negative current, which is essentially telling you that the current is in the same direction as the migration of holes. So, this is the diffusion current density for electrons, and we define the diffusion current density as JDF comma n for electrons and JDF comma P for holes, and dn is the diffusion coefficient for electrons and dP is the diffusion coefficient for holes. And and it is useful to note this relation, and we can sort of derive this, and I will show that to you in a little while. So, dn is kT mu by q. Okay. So, this relation is something called as the Einstein's relation. In order to understand how Einstein's relation comes about, all you need to do is take any situation. It is not just limited to carriers in a semiconductor. In any situation where the carrier count follows a Boltzmann's distribution, in the sense that n scales is proportional to e to the power minus a potential. So, let us say q phi by kT, or let us say it is minus phi by phi naught. Okay. So, if you have a Boltzmann's like distribution where n is say some n naught e to the power minus phi by phi naught, where phi is a potential, you will end up with the Einstein relation being valid. Okay. Just to derive it, so if you take our charged carriers itself, our carriers, the electrons and holes in a semiconductor, when left alone, okay, at thermal equilibrium, you need to have, if there exists any drift current, it must be completely balanced out by the diffusion current. Okay. So, at thermal equilibrium you cannot have currents, and if there is a drift current, it must be balanced out by diffusion current. And using that as a starting point, you need to have your q. Let us only take electrons as an example. Let us say electrons are the only carriers. So, you need to have q n mu electric field matching your diffusion current, which is q dn by dx. Now, if n follows a Boltzmann's relation, say n is equal to some n naught e to the power minus phi by, let us say instead of thermal voltage we will just call it some phi naught, which is a constant, your dn by dx is equal to n naught e to the power minus phi by phi naught alright, into minus d phi by dx, okay, and your electric field is equal to minus d phi by dx. So, you substitute these two in this particular expression here, and you will end up with a relation q n mu d phi by dx, okay, let us get rid of the negative sign, is equal to q dn n naught e to the power minus phi by phi naught is again n. So, n d phi by dx. So, the term n and d phi by dx cancel out, okay. And sorry, I missed out a 1 by phi naught term here, okay, and okay. So, you take into account the 1 by phi naught, okay. So, you end up with dn being equal to let us just bring that in right here, being equal to mu into phi naught. Now, if phi naught is a thermal voltage which is kT by Q, you will end up with your dn being mu kT by Q, which is your Einstein's relation. So, that is the way this relation comes about, okay. So, the diffusion coefficient is very much connected to the mobility of carriers. So, now let us look at the total current, okay. So, we have identified the two mechanisms, you have drift, okay, and you have diffusion. In the case of drift, we found that the electron and hole currents add up, okay. The electron currents and the hole currents add up to give you the total current, but in the case of diffusion, for the same profile, the effective current was in the opposite direction. So, if you want to define the total electron current, okay, it is the current due to drift plus diffusion of electrons. The current due to, so let us take this profile here, okay. So, you have dn by dx greater than 0, and let us say we apply an electric field in this direction, okay. So, all the electrons will move from right to left because of the applied electric field, okay, and all the electrons will move from right to left because of the concentration gradient. So, which means that the drift current where the driving force is the electric field, and the diffusion current where the driving force is the concentration gradient, both exist in the same direction and they both contribute to the current. So, J drift plus J diffusion for the electrons is going to be the summation of Qn mu n into electric field plus Q dn by dx to give you the total electron current density. But for holes, we have the same situation, you have dP by dx greater than 0, you have the electric field which is the driving force for drift pointing in the same direction. But what happens is that the hole flux due to the concentration gradient is towards the left, because there are more holes here as compared to here, and the hole flux due to the field is going to be along the direction of the field. So, it is going to move from right to left, and therefore, these two are against each other, and therefore, the total hole current is going to be the total drift current due to holes plus the diffusion current due to holes, but the diffusion current has got a negative sign, and therefore, you have Qp mu p into electric field minus Q dP by dx being the total effective current due to holes. So, that is a quick summary of the different current mechanisms.